Good morning, everyone. So today we will start with chapter 10, in which we are going to study the rotation of rigid bodies around a fixed axis. So let's start first by looking at the outline. In this new chapter, we are going to deal with the variables we already defined and presented in very early chapters when we were studying the translation. But in this case, we will define them in a new form by looking at the rotation instead of looking at the translation. And so this is why we call them the angular variables. And in these angular variables, we will see the angular displacement, the angular speed given by omega, and the angular acceleration denoted by alpha. We will also see the relation between the linear variables, which we know as the velocity vector and the acceleration vector, with the angular variables omega and alpha. We will review the kinetic energy of rotation, what is the moment of inertia of a given object, and the parallel axis theorem, the torque, Newton's second law for rotation. We'll also review the kinetic energy theorem, the work kinetic energy theorem in the case of a rotation, and finally the rolling motion of rigid body. In what concerns the rolling motion, this will not be covered in this PDF file. We will discuss this topic later. So to study the rotation of rigid body about a fixed axis, let's first start by defining what is a rigid body. And actually, the easiest way to define it is by saying that a rigid body is one that is non-deformable. So the relative locations of all particles that constitute this object is these relative locations and positions remain constant. So in other words, when a rigid body rotates about a given axis, its shape will not change, and the position of all the particles relative to each other also will not change, they will remain constant. For the fixed axis, of course, it's clear for everyone what does it mean. It means that you have an axis about which the rotation is occurring, and this axis does not move in space. If you want to be rigorous and realistic, we should say that all bodies and all objects in our real life, they are not rigid in a perfect way. So when we say rigid body, we mean that we modelize an object as a rigid body because its deformation is quite negligible when it makes a rotation, and this model is quite useful to describe this kind of situations. So as an example, when we in all this chapter, throughout this chapter, we will be discussing this kind of case where we have a body of arbitrary shape or form, and it's rotating around an axis. In this case, it's the z-axis. And this axis, we call it the rotation axis, the axis about which the rotation is done. Now, if you look at this body, every point and every particle of this object, when this body, it rotates, the particles, they will be undergoing so if you look at this particle, for example, it will be undergoing a rotation about the axis. So in other words, that means that it will be traveling along this circle, okay? And the radius of this circle would be the distance between the point in here and the rotation axis, which is over there. So this is the radius of this circle along which the particle, a given particle P, is moving. And we have also to make sure and to understand that all these particles, they rotate through the same angle. So if you look at another particle, for example, like this particle in here, let's call this Q, for example. So when this object will rotate about the z-axis, Q will be moving on a different circle, because in this case, the circle is defined by the radius, let's call it R prime. And this R prime is the distance between Q and the axis, rotation axis. So it should be smaller than R, as we can see from the figure. So this is the circle along which Q is traveling when the body rotates about the z-axis. And this is the circle along which the particle P is traveling when the body rotates. Now, if we have a look from top, let's consider that the body, it rotates through some angle. Then we'll see that the point P will move a given arc of circle along this circle. okay, and it will travel this arc of circle, and this angle would be the angle through which it has rotated its d theta. And in the same way, if you look at Q, you will also see that Q will also travels along this circle, a given arc of the circle, and it will also rotate through the angle d theta. Now the point is that all particles of this body will rotate through the same angle d theta if the object rotates through the angle d theta about the z-axis. Now let's move on. And let's define the position, the acceleration, and the velocity in the case of a rotational motion. So let's, for this task, let's consider a compact disk that is rotating about the fixed axis through O. So this is the disk. The rotation, it occurs through an axis that passes by this point O in the center. Okay, and let's consider an arbitrary point about this disk. So let's take this point P to be our point, which we are going to study. Of course, it's convenient in this case to represent and to describe the position of the point P with two new coordinates that you know, which are the polar coordinates. So in other words, if this disk will make a rotation, let's say in this direction, then obviously the point P will move on its circle. So the circle on which the particle P is moving is this kind of circle in here, with a radius given by r. So if the disk will rotate through a given angle, then the point P will end up in this position, in this new position in here. And in this case, we say that the particle P has moved through an angle theta. So مشيت على نفس السيركل، فإذا الآر ما تغيرت عمليا، the distance between the point and the axis of rotation، وإنما يتغير بالنسبة للبوزيشن الأساسية والبوزيشن الجديدة إنه في angle بيناتهم which is given by theta. So r is the distance then from the origin to the point P, and by the origin we mean the axis of rotation, and theta is measured counterclockwise from some reference line. So if we take the initial position of the particle to be our reference line, and then going up from this reference line, we measure theta in a positive way. counterclockwise لأنه بعكس اتجاه عقارب الساعة. So when P, just like all other particles in this body, undergoes a circular motion, only the angle theta changes in time, because as long as P is moving, r is all the time the same, because r is the radius of the circle and it's not changing. So only theta changes as a function of time. And so we can say that the particle P, it moves through an arc of circle that we are going to call S. This arc of circle is related to the angle theta through the following relation. S is proportional to theta, and the coefficient of proportionality is the radius of the circle. So this is why we can use this relation to relate S to theta, or also we can say that theta is equal to S divided by r, where r is the radius again. And actually, theta is expressed in units of radian. So as you can see in here, theta is equal to S over r, where the unit of theta is simply the radian. Now, a few comments about the angular position. First of all, because the disk is a rigid object, then as the particle moves along the circle from the reference line, every other particle on the object rotates through the same angle theta. So if you look, for example, at any other point, like a point which was over here, for example, if you look at this point that we are going to call Q, for instance, and so this is the initial position of the point Q. Now, if in this position in here, when P has traveled an arc of circle S that corresponds to an angle theta, you will all see that the point Q will travel exactly the same angle. So it will travel an angle is exactly equal to Q, and we will find at the end of the day Q at this point, at this new position in here. ومش بالضرورة تكون يعني it's R prime. The distance between Q and O is R prime, that is different than R. However, as long as the disk is rotating, all the points move through the same angle. So this is why we can associate the angle theta with the entire rigid object, as well as with the individual particles. So we can say that each particle is moving through the angle theta, but we could also say that the whole rigid body is rotating through the angle theta. The angular position of the rigid body is then only given by the angle between this reference line and the fixed reference line in space. So this reference line that we called, this in orange, it's the line between the origin, which is the axis of rotation, and the point we are looking at. And the fixed reference line is usually taken to be this line, which coincides with the x-axis directed in the positive direction, so to the right. And the rotation, of course, it can occur in two possible directions. يا اما بهالاتجاه هيدا, in this case we can call it counterclockwise, or it can occur in the opposite direction, so in this way, and we call it then clockwise. So the rotation in general, it can occur in two different directions, counterclockwise or clockwise. Now, how can we define the displacement in the case of rotation? That is very easy. We know that displacement is defined as the difference in the position. And when we talk about the rotation, we already said in the previous slide that the position in such a case, in the case of rotation, is defined by the angle theta, basically. So this is why when we say that the object is rotating and we have an angular displacement, this angular displacement is defined as the difference between the final position minus the initial position. And so the final position is the final angle through which the particle has rotated, and of course theta initial is the initial value of this angle so it's the angle of the particle in its initial position. So let's consider in particular this example. So the disk rotating counterclockwise with the point P on it, moving through this arc of circle S that corresponds to this angle theta. So for example, if we take just 2 times T initial and T final, okay, let's say the point P was initially at the position A at the time Ti, and this position is defined by theta I with respect to the x-axis, which is our reference line. Now, if the disk has rotated through a given angle delta theta, then that means that the particle P will travel through this arc of circle. The radius of the circle is of course the same, doesn't change, and at the time T final it will end up with a position defined by the angle theta F with respect to the reference line, that is the x-axis. And so we said that the reference line of length r has swept out an angular displacement delta theta, which is equal to theta final minus theta initial. So عمليا the difference in the position هو الفرق ما بين الفاينل بوزيشن ثيتا فاينل minus الانيشال بوزيشن ثيتا اي, and so هيدي هي الدلتا ثيتا يلي عم نحكي عنها. This is the extra angle that the point P has traveled when the disk has rotated. So delta theta is of course the same for all individual particles as well as for the entire rigid body. Delta theta, it can be positive or negative, of course. It is positive if the motion is occurring in the counterclockwise direction, and it's negative for clockwise motion. Because as we said, we measure theta in a positive way when we go up from the x-axis, يعني لما نكون ماشيين counterclockwise.